Welcome to Basic Mechanics, a Critical Look, Lecture 3. In the previous lecture, we had introduced the notion of an inertial observer, a special kind of observer for whom Newton's first law works. The reason why inertial observers are important is that the laws of Newton, in particular Newton's second law, can only be used if the observer is inertial. Hence, any proof or purported proof of Newton's first law from Newton's second law is bound to be fallacious or circular, simply because you will have to start by assuming Newton's first law works if you are going to use Newton's second law at all. Now, the important question that we are going to try to address today is the following. Is Newton's first law just important as a definition of an inertial observer? After all, a definition is just a name. It's a convenient name. We define something in science because it is going to be convenient to use the name rather than the whole concept. And we will need to use it over and over again. So definitions are important. But basic physics laws are not necessary for definitions. And if all that Newton's first law had really done is define an inertial observer, then it would really not be that important as a basic fundamental law of physics. Now, to see exactly why Newton's first law is much more than the definition of an inertial observer, let us first address the question, how does one find inertial observers? Now, we have a very common answer that is given to this question, which is the following. An observer who does not accelerate is inertial. Now, this is quite fallacious. It's common, but fallacious. Simply because when you say does not accelerate, it begs the question, with respect to whom does this observer not accelerate? After all, I am always going to be stationary with respect to another observer who is stationary with respect to me. And I am always going to accelerate with respect to another observer who is accelerating with respect to me. So, does not accelerate is a very observer-dependent statement. You cannot really say that one observer is inertial and the other one is not, based on whether they accelerate with respect to some particular observer or the other. Before we move on to the actual answer to how one finds an inertial observer, we should take a look at exactly where does this particular wrong answer come from and what does it really mean in the context of inertial observers. Now, this is something we had already discussed in the last lecture, but let me just repeat this once again. Suppose you have two different observers O and O prime with their own set of Cartesian coordinate axes x, y, z and x prime, y prime, z prime. The axes are not rotating with respect to each other. In particular, I have assumed that x and x prime are parallel to each other, y and y prime are parallel to each other, and so are z and z prime. This last assumption is strictly speaking not essential, but makes life a bit easier. Now, if both of these observers were to observe the same point particle P, then the position vector of P with respect to O would be this vector R drawn from the origin that O uses to the point P, and with respect to the observer O prime, the position vector of the point P would be the vector drawn from the origin O prime to P, that is this vector R prime. And it's obvious that this vector R is the sum of this vector O prime, which is the position vector of the observer O prime with respect to O, and this vector R prime. So we have R vector equals R prime plus capital R. Now we are also going to assume that the two observers use the same time. In fact, we will have a lot more to say about this issue about time later. For the time being, let's just assume that they use identical notions of time, and then derivatives calculated simply gives you dr vector dt is dr prime dt plus capital R dt, which translates to velocity of the point P with respect to O, v, is equal to v prime, which is the velocity of the same point P with respect to the observer O prime, plus VO, where VO or V observer stands for the velocity of the observer O prime with respect to O. One more differentiation and you end up with the result. d2r vector dt2 is d2r prime dt2 plus d2 capital R vector dt2, which tells you that the acceleration as measured by O of the point P is equal to the acceleration as measured by the observer O prime plus the acceleration of O prime with respect to O. These are simple, straightforward relative velocity and relative acceleration calculations in classical physics. Now, what is very important is that in general, A and A prime will differ, but if A observer happens to be 0, if the observer O prime, irrespective of whether it's moving with respect to O or not, is not accelerating with respect to O, then you have A observer equals 0, and O prime will then measure the same acceleration of the point P. So if it so happens that observer O is inertial, that is F is equal to ma as far as observer O is concerned, then since O prime measures the same force F and the acceleration A prime is the same as A, you are going to get F equals ma as a valid equation for O prime as well. So, if observer O happens to be inertial, then so is O prime. So when you say an observer who does not accelerate is inertial, what you really mean is an observer who does not accelerate with respect to another one who is known to be inertial is inertial. Now in this discussion I have left out the possibility of the axes of the two observers rotating with respect to each other. If that happens, things become even more complicated, but we can simply say that the observer O prime will be inertial if it translates with respect to the observer O with uniform acceleration, with the important proviso that O is already known to be inertial. So if you can find one inertial observer, you can find an infinite number of them. Just find another observer who is not accelerating with respect to that one, you have found your new inertial observer. So the notion of does not accelerate is actually an important concept here, but it still does not answer how do we find an inertial observer, because at this stage we do not know how to find that first inertial observer. So the real question now is, how do we find the very first one? And to answer that, we have to fall back on the definition of the inertial observer. An inertial observer is someone for whom Newton's first law works. That means it's an observer who observes an object on which no force acts to be acceleration free. So in order to decide whether an observer is inertial or not, what you need to do is find an object which does not have a force acting on it and check whether that observer sees that object to be acceleration free. If she does that, then she is inertial. If she does not, that is, if she finds a force-free object is accelerating with respect to her, then she is not inertial. Now it all sounds very straightforward until you realize that figuring out whether a particular object is force-free or not is not really as simple a matter as it seems. To see why I am saying that, let us fall back on our favorite example, that of a box resting on a table. In the lecture where we talked about this, we said that the box is force-free. But really, is it force-free? It is definitely not true that there are no forces acting on this box. There's a force of gravity acting downwards. There's also a force, the restoring force exerted by the table. So you have two forces, W and N. Now when I say the box is force free, what I implied was this. The two forces were equal and opposite and they cancelled each other out. But how do we really know that they actually cancelled each other out? For that we had to fall back upon the fact that the box was not accelerating with respect to me, and hence I was using at the back of my mind Newton's first law. Because the box is not accelerating, the automatic assumption was there is no net force acting on it, and the only way that can happen with both W and N being present is that these two forces balanced each other out. But note that here I am already assuming that Newton's first law works for me. I cannot use that to prove that I am an inertial observer. I have already assumed that I am an inertial observer in this case. And this should become even clearer when you consider the situation where this box and the table on which it rests was in a downward accelerating lift. In such a case, of course, W and N did not balance each other out. But if I were standing next to that box, I would still see the box not accelerating. It's only when I look at it from the outside of the lift that I know that the box is accelerating, and then I would be able to figure out that W and N did not balance each other out in that case. The question is, how am I so sure that they balance each other out when I'm just standing next to a table in an ordinary room? The only way I could really argue that was by using Newton's first law, and that of course cannot be used to justify that I am inertial. That would be a circular argument. A little thought should convince you that in all the cases where we say that an object has no net force acting on it, what we are really doing is arguing from the fact that we do not observe the object to accelerate, the fact that it has no net force on it, but there we are actually using Newton's first law already. Something that cannot be used to prove that the observer is inertial. So we are now actually faced with this rather deep question, how to ensure that an object is force-free. And the way Newton settled this question was simply by saying that the only way an object is guaranteed to be force-free is if it is very, very far away from all other objects. So an object which is distant from everything is guaranteed to be force-free because all forces fall off with distance. Now, this gives us a clue to how to figure out the very first inertial observer. An object which is very, very far away from all other objects. Newton had an example of that, and that example was that of a distant star. Now for these distant stars, which were also distant not only from us but from all other stars and other objects, the net force acting on them would simply vanish, not because of any other reason but because of the fact that they are so very far away from all possible force creating objects. So now, Newton's version of an inertial observer, at least the primordial inertial observer, the one you must start with, was the following. An observer is inertial if it observes a distant star to move with uniform velocity. Now there's one obvious way in which this can be guaranteed. All you have to do is fix the observer with respect to the distant star. Now, fixing it to the distant star may be a bit problematic, both because the distant star really is distant, and also if you were to fix something to a distant star, then that observer might actually exert a force on the distant star itself. Of course, you can always assume that your observer is a body with zero mass and cannot exert a gravitational force on the star, but even that is not necessary. Your observer could very well be right in your vicinity somewhere, but fixed with respect to the distant star. And then that distant star will obviously not move with respect to the observer. It is force free by virtue of being distant and acceleration free rather trivially, because it's simply not moving with respect to our observer. So we have found our first initial inertial observer. And of course, once we have found one inertial observer, we have actually found infinitely many, because any observer who translates with respect to this one with uniform velocity is automatically inertial. So it seems that our problem has been settled. We have a prescription by which we can figure out our first inertial observer, and from that point on, all inertial observers. Indeed, if it so happens that an observer in my vicinity, let's call that observer O, sees a distant star accelerate with an acceleration A, then O is of course not inertial, but you can very easily produce an inertial observer by simply considering another observer O prime who is translating with respect to O with the same acceleration. Now, what will happen is O prime will observe the distant star to have zero acceleration with respect to it, and hence, even without necessarily being fixed to the distant star, you can guarantee that you have an observer, O prime, who sees the distant star to be not only force-free, but also acceleration-free. Now, if this were the entire story, then Newton's first law would give us a very nice and almost trivial prescription for figuring out which observer is inertial. And then, of course, once we have done that, we know whether we can use Newton's second law for that observer, and we can go ahead and do whatever we want to do with it. At this stage, you might be relieved that we have finally sorted out the problem of finding inertial observers. But if you are paying attention, then this should also come as a bit of an anticlimax. Not just a bit, it should come as a pretty big anticlimax. After all, we have been claiming that Newton's first law is a very basic law of physics, and it's one which is perhaps one of the most important laws that human mind has ever thought of. But if you see it in this light, it seems to be nothing more than a prescription about how to find an inertial observer. And there, we see that ultimately, it is pretty easy to find one. All you have to do, as we just said, is fix somebody with respect to a distant star. Something that can always be done. If this was all there was to it, then Newton's first law would not really have been an important law at all. In fact, it wouldn't even have perhaps deserved the name of a law of physics. It could just be a prescription for finding inertial observers. Now, the important point that must be emphasized here is Newton's first law would really be trivial if there were only one distant star in the universe. Because then, all we would have to do is fix our observer with respect to that distant star, and that observer would be guaranteed to be inertial. That is really a trivial statement to make and not something deep to say about the universe. However, given there are many distant stars, what is the guarantee that all of these distant stars will move with uniform velocities with respect to the same observer? This prescription that we have given will definitely render our one distant star acceleration free. But what about other distant stars? Isn't it possible that they might accelerate with respect to the observer that we have found? Now, the statement that is being made here is exactly a guarantee about the nature of the universe. The guarantee that you can find an observer with respect to whom all distant stars will be acceleration free is exactly Newton's first law. So what really gives Newton's first law non-trivial physics content makes a statement about the way the universe is, which the universe did not have to be by definition, but happens to be, is the following. There exists inertial observers. There are observers with respect to whom all distant stars are acceleration free. Now this in itself is a very, very deep statement. But as we will see in the next lecture, even at this stage, it only scratches the surface of how deep Newton's first law really is. We will see that Newton's first law gives us a prescription for figuring out the nature of a very, very mysterious entity. Time. But since at present we are short of that very same entity, we will have to wait for the next lecture for a discussion on that. Bye for now.